Our final video that deals with the kinetics chapter is dealing with the math associated with the Arrhenius equation. So our last video kind of focused on relating the ideas of a mechanism, of collisions, of a reaction having to progress to the important components of the Arrhenius equation, which include activation energy. What we're going to do now is we're going to get back to a mathematical description of things, and we have this Arrhenius equation that looks kind of familiar in its functional form, and we're going to do a lot of different manipulations today that feel familiar. And we're going to introduce two types of problems that you'll see related to using the Arrhenius equation in a mathematical way. Okay, so first let's start by writing the equation down again. Try to memorize it if you can. The Arrhenius equation looks like the rate constant is equal to A, e to the minus e sub A over r, and then 1 over t is also up here. We know that this is an exponential form, okay? And we've seen exponential forms before. We saw them with first order kinetics in the integrated rate law. We saw them with vapor pressure. And the connection I'm gonna make over and over again today is that everything that we did with vapor pressure, because it feels the same in terms of the mathematics, if you kind of got what we did with vapor pressure and you understood what the mathematics were there, they're the exact same things that we'll be doing here. So when we introduce this idea of a negative exponential of a decay in the context of vapor pressure, one thing that we did is we kind of knew that we could take it and we could linearize it. Same thing with first order kinetics. So what we're going to do is we're going to start with our Arrhenius equation, which is a good form to know, but I want to kind of build a line equation from this. So I'm going to take the natural log of both sides, and again, the impetus for doing that is that I see that I have this exponential there. So I'm going to take the natural log of both sides. I'm going to get a natural log of k here. Here I'm going to get the natural log of a e to the minus e sub a over r, 1 over t. Inside here, we have the natural log of things being multiplied by each other. So I'm going to rewrite this as the natural log of a plus the natural log of e to the minus e sub a over r, 1 over t. All right. So all we're doing is we're using that log rule where if there's multiplication inside a log, you can write it as the addition of two logs together. Oh, well, I also know that when a natural log finds an exponential, they cancel each other out. So I'm just going to do a little bit of rearranging. Natural log of k equals, oh, that cancels out. So what I'm left here is minus e sub a over r, 1 over t. All right, I'm going to write that in front. Minus e sub a over r, the natural log and the e are gone, times 1 over t plus the natural log of a. And now you can see why we wanted to write it into this form. We see this familiar line form manifest from our analysis. This looks like y equals mx plus b. Looks like y equals mx plus b. So, wait a second. We just got done watching a video where activation energy is incredibly important. So how could we possibly determine activation energy? So you can make a reaction coordinate potential energy diagram, but that's not always practical. From the standpoint of what we do experimentally is we often calculate E sub A so that we can draw our diagram correctly. So how could we calculate E sub A? Well, what we can do is we can monitor K and how it changes with temperature. And if I look at that change, I know K is going to go up as temperature goes up for reasons that we discussed already. If K goes up as temperature goes up, well, hold on a second, I can linearize this. And if I take the K's that I get and I make them the natural logs, and I put them on my y-axis, and I take my temperatures, right? And I invert them, and I remember that temperature has to be in Kelvin and all that, and I make them my x's. So I have this set of y's that I build from my k's, turning them into natural logs. I have these set of x's that I build from my t's, doing 1 over t's, right? If I make that plot then, I should see a line. And that line has, importantly, as the slope minus e sub a over r. And minus e sub a over r, okay, r is known. All right, so if I can get my slope, I can get to e sub a, right? Real important idea. So it brings up another type of problem that you see that you actually have to enact a graphical analysis for. If you're given a set of k's and t's, what are you going to do? You're going to take those and you're going to make natural logs of k's. You're going to take your t's, you're going to make 1 over t's, right? You're going to make a plot, and the slope is minus e sub a over r, okay? So if you pull up the files I sent way back at the beginning of the semester dealing with kinetics, so if you pull up your kinetics PowerPoint, what you'll see is there's 2 important slides that we're going to kind of reference here. I'm just going to hold them up to the camera and try to just convey the information that way. But if you have those slides from the slideshow, that's exactly what I'll be showing you now. So what I'm going to show you here is with this problem on the slideshow, I essentially give you a set of t's and k's. That's the starting point. What we see is that as t increases, k is getting bigger and bigger and bigger. Okay, that makes sense from the modeling stuff that we talked about earlier, all right? What I show over here is, okay, yeah, the thing that you have to recognize is when I get t's and k's, what I have to turn them into is I have to turn them into inverse temperatures, right, in units of inverse Kelvin, and I have to turn them into natural logs of k's, right? Because if I do that then, and if you flip to the next slide, what I can make is I can make a graph. And on that graph, I can determine activation energy, right? So again, I left this graph not labeled, but we should be able to see from our analysis and what we've written in our notes that the natural log of k is actually going to be on the y-axis, and that's unitless. The x-axis is going to be 1 over t in units of 1 over Kelvin, right? Natural log of k on the y, 1 over t on the x. And we see that we get a line out. And it's not like a test, it's not like our rate equations that we're using, our integrated rate laws where we have to do 3 different graphs. Nope, there's just 1 graph to make. If you look at the line, all right, there should be a slope involved there, and that slope contains the activation energy information. And that's how we're gonna proceed with this problem. So if you look at that slide, what you'll see is from enacting this graphical analysis for the example given, the slope comes out as a number. And we're going to finish the example together here. And the slope that comes out with that number, the slope that Excel gives us is the slope equals minus 1435.7. We're going to use 2 significant figures because in our data, it makes sense if you go back and look at the data to use 2 significant figures. If that's confusing, just make sure you analyze the data and think about actually calculating a slope and having a difference there, right? So that's where we're left with the slope. Slope is missing one thing, it's missing units. If I go back and think about where this slope had to come from, slope is change in y over change in x. I'm just going to write this off to the side. From our graph, our y's were natural logs of k. So from a unit perspective, there's no units there. So I'm just going to put a 1 there. Our x's were 1 over t in 1 over Kelvin. All right, so the units down here are 1 over Kelvin. And I know I ask this question a lot, but what's 1 over something? It's that something. So if I think about the slope calculation, what makes sense for units is that the units must be Kelvin. So this is minus 1435.7 Kelvin. That's the slope. From our understanding of the linear equation that we wrote down before, this is equal to minus E sub A over R. So if I want to solve for E sub A, what I can do is I can rearrange this equation. E sub A then, if I'm going to solve for this, I'm going to take the negative to this side. It's going to cancel with that. This is going to become positive. That's good because my E sub A should be positive because it's a hill. If you ever get an E sub A that's negative, check for a sign error. Valleys don't make sense for hills, all right, for E sub A's. If E sub A is a hill, it should be positive. So E sub A becomes positive because of the negative and negative. Oh, and then I have to take R and multiply it by this. So I'm going to have 1435.7 0.7 with two significant figures, Kelvin, times 8.315 joules per mole Kelvin. And then what we'll see here is we get out units that make sense. The Kelvin and the Kelvin cancel. Let's plug this into your calculator. All right, you can pause here and just check that you can carry out this mathematics yourself. What I get at the end is I get 11,000. All right, 11,000, that's a comma. All right, 11,000 joules per mole when I round to two significant figures. Now this means that it's 11 kilojoules per mole. And if you remember the axis that we had in terms of the units on our potential energy reaction coordinate diagram, the axis there was kilojoules per mole, right? So E sub A is something we could pull off of there and relate to that axis. So getting units of kilojoules per mole makes perfect sense. So that's great, right? So here, that E sub A, that was really important with all the last discussion that we had. This is the way that we can calculate. We can calculate it graphically. There's one other way we can calculate E sub A. And this goes back to, again, stuff that we're familiar with from how we dealt with vapor pressure. Now for vapor pressure, we didn't often refer to it as a graph. When we did with vapor pressures, we knew we could make a line, but then we made a two-point equation. So when we looked at the Clausius-Clapeyron equation, we called it a two-point equation. We can do the same thing here with our Arrhenius equation. Again, hopefully this feels familiar. If you want to kind of take a stab at doing this yourself, what we're going to do next is we're going to derive the two-point form of the Arrhenius equation. See if you can do it yourself, right? I'm going to do it now for us or with us together. What I'm going to do is I'm going to write down 2 points. So I'm going to use the linear form. I'm going to write it down twice. So natural log of k, let's do 2 to start with, equals minus E sub A over R, 1 over T2 plus the natural log of A. Oh yeah, something that I forgot from before. Sometimes graphically we want to determine what A is. Here's a linear equation. We just figured out how to use the slope to get E sub A. What's the y-intercept? The y-intercept is the natural log of A. So if you're after that Arrhenius parameter, if you're after that information about how big something is in terms of molecular structure for the collision, it's inside there, all right? We kind of do that less often, but I know some of you are going to have lab that might have you do that. Just remember the same ideas from actually using a line equation and getting a y-intercept, they apply for this equation as well. All right, I'm going to write this again, but I'm going to use a different temperature, so K is going to change. A stays the same, E sub A stays the same, but K changes as T changes. So I'm going to write natural log of K1, and again the 1 and the 2 there, just labels, looks like minus E sub A over R, 1 over T1 plus the natural log of A. What I'm going to do next is, just like before when we did Clausius-Clapeyron, we're going to subtract. So I'm going to subtract here. This becomes positive. This becomes negative. I'm going to bring these guys together. When I do that subtraction step and I bring them together, notice the natural logs of A cancel out. Okay. I have a subtraction of natural logs. All right. Oh yeah, I know the natural log of K2 minus the natural log of K1. I can write that as the natural log of K2 over K1, just like we did with PVAP in Clausius-Clapeyron. Over here, I'm going to pull out a negative E sub A over R. If you look at each one of these terms, they're going to have an E sub A over R. I'm also going to pull out the negative sign, so I can write this as 1 over T2 minus 1 over T1. And then you're done. This is the two-point form of the Clausius-Clapeyron equation. And it looks exactly from a form perspective, this is a two-point form of the Arrhenius equation, and it looks exactly like our two-point form of the Clausius-Clapeyron equation we had before. Again, this K, this first one that you write up here, it's tied to this T. There's a negative sign out in front. That also means that this K that's on the bottom is tied to this T. What units does your T have to be in? They have to be in units of Kelvin so that everything works out. And I don't really even need to go through an example of how to use this because we already did a bunch of examples earlier in the semester with how to use the two-point form of this type, and it's the exact same process. There's 1, 2, 3, 4, 5 unknowns. you're going to be given questions where one of these guys will be unknown. And so what you do is you substitute everything else in, pay attention to significant figures, pay attention to your units, and solve for the other unknown, right? So the mathematics are actually not unfamiliar. They're familiar to us. They're something that we've seen before. And so have some confidence that if you kind of got that Clausius-Clapeyron stuff, you'll get this as well. Quick little review. The mathematics associated with the Arrhenius equation, getting that important E sub A information off of, or for a reaction from experimental data, involves relating K to T, not necessarily in the exponential form, but linearly. If I plot natural log of K and 1 over T, I'll be able to make a line whose slope is related to E sub A. I could also do a 2-point equation, and I could build this mathematical equation with 5 unknowns, where if I can make 4 measurements, I can solve for the other unknown. All right. So that's the math involved, and those are the types of problems you'll see. How do I know to do the graph that we just went over from the slideshow versus using this, right? For the graph, you'll need to be given a set of K's and T's, and then you manipulate from there. For this, it's gonna be like a word problem, and it looks like, oh yeah, I'm relating E sub A to temperature to K, right? There's no list, there's no table, it's just this relationship that they want you to go through, and you set this up and you do your check marks, and there's one unknown, and you solve for that one unknown. Okay, so that's it for kinetics. The next thing we'll talk about is equilibrium.